Nerds, Twizzlers, and Haribo candies are created through an absolutely fascinating factory process few have got to see. Behind the sweetness is a high-speed factory process, turning sugar and color into some of the most popular treats on Earth. Today we're stepping inside the production lines to see exactly how these candies are made from start to finish. The history of Nerds stretches back to the early 1980s, when they were first introduced to the market as a playful, intensely flavored treat unlike anything else in the candy aisle. The appeal lay in their irregular shapes, their bright colors, and their signature combination of sweet and sour notes. Behind the scenes, however, the magic is created not by whimsy, but by a carefully controlled industrial process. It all begins with the sourcing of raw ingredients. The foundation of Nerds is refined cane or beet sugar, which arrives at the factory in bulk deliveries, often in multi-ton silos or in large paper sacks that are emptied into storage hoppers. This sugar is highly refined to ensure purity, with a moisture content so low that it will not clump during storage or handling. Alongside the sugar come shipments of corn syrup, which acts as a binding and texturing agent, as well as citric acid and malic acid to provide the tartness that defines Nerds' flavor profile. The plant also receives concentrated flavor oils and powdered colors approved for food use. Each batch of these ingredients is tested in a quality control laboratory before it enters the production stream, ensuring compliance with both flavor and safety standards. The production of Nerds begins with a core, which is essentially a tiny granule of sugar that serves as the seed for the candy's build-up process. These seed crystals are often derived from slightly coarser sugar grains that have been screened to a uniform size. The real artistry begins in the heart of the coating pans, large rotating drums that are the beating heart of sugar candy manufacturing. Inside these stainless steel pans, the sugar seed crystals are gently tumbled as a fine mist of sugar syrup is sprayed over them. This syrup is prepared in a heated mixing tank, where granulated sugar is dissolved into water under controlled temperature, often in the range of 110 to 130 degrees Celsius, and then blended with a precise amount of corn syrup to control crystallization. The hot syrup flows through jacketed piping to prevent premature cooling before being atomized into a fine spray within the coating pan. As the syrup coats the tumbling seed crystals, it begins to harden upon contact with the cooler air inside the pan, forming a thin outer layer. Then, a light dusting of dry sugar is sometimes added to further build the surface and maintain separation between individual granules. This cycle repeats dozens or even hundreds of times, each layer adding microns of thickness to the growing candy piece. Operators closely monitor airflow, humidity, and drum rotation speed to ensure that the candies do not stick together or form unwanted lumps. During this stage, the irregular shapes that make Nerds so distinctive begin to emerge. Unlike machine-molded candies that have identical geometry, these sugar-coating pans produce slight variations in size and contour, which means every Nerd has its own unique outline. The gradual layering process continues until the candy reaches the target size, which is typically just a few millimeters in diameter. Once the base size is achieved, flavoring and coloring are introduced. This is a delicate operation, as liquid flavors and colorants must be distributed evenly without dissolving the sugar surface. The pan operator reduces airflow slightly and sprays a concentrated solution of flavor oils, acids, and color onto the candy bed. In many cases, flavors are applied in small incremental sprays with pauses for tumbling in between, allowing the surface to dry and preventing color streaking. The flavors are carefully balanced so that the acids provide tang without overwhelming the sweetness, creating the signature taste that fans recognize instantly. After flavoring and coloring, the candies undergo a polishing step. This involves applying a thin layer of glazing agent, such as carnauba wax, which gives the Nerds their characteristic sheen and helps protect them from moisture pickup during storage. The glaze is applied in a separate polishing pan, where candies are tumbled with a small amount of the molten wax until every piece has a uniform shine. At this point, the candies are allowed to cool and set fully, ensuring that their coatings have hardened completely. Cooling may occur in ambient air or in a temperature-controlled chamber that maintains low humidity to prevent stickiness. The fully cooled candies are then transferred via gentle vibratory conveyors to the packaging area. The packaging operation for Nerds is an impressive example of precision weighing and high-speed filling. Because the candy pieces are so small and irregular, multi-head weighers are commonly used to ensure accurate portioning. These machines use multiple load cells arranged in a circular pattern, dropping small amounts of candy from each channel until the combined total matches the target weight. This system minimizes giveaway and ensures that each box contains exactly the promised amount. The iconic Nerds boxes are constructed from food-grade cardboard with an inner lining that protects against moisture. The packaging line begins by folding and gluing the flat-printed cartons into their box shape, often with automated carton erectors that can handle hundreds of units per minute. The weighers then deposit the precise quantity of candy into each box through stainless steel chutes. For dual flavor boxes, a partition is inserted inside the carton, and two separate weighing heads feed different candies into each side simultaneously. Once filled, the boxes pass through a closing station, where flaps are folded and glued shut, followed by a coding station that prints lot numbers and best before dates for traceability. The sealed boxes are then collated into larger trays or shrink-wrapped bundles for ease of handling in distribution. Quality control continues all the way through the process. In addition to the raw ingredient checks at the start, samples of candy are pulled from the line at regular intervals to assess flavor consistency, color uniformity, and physical integrity. The hardness of the coating is measured with specialized instruments, and the acidity levels are checked to ensure the sourness remains within the brand's signature profile. Metal detectors are integrated into the conveyor system to ensure no foreign materials make their way into the final product. From the packaging area, the candies move to the warehouse for distribution. Since Nerds are low in moisture and have a hard sugar shell, they are relatively stable during storage. However, they are kept in a cool, dry environment to maintain their texture and prevent color fading. Pallets of finished product are wrapped and staged for shipment to wholesalers, retailers, and export markets around the world. The journey from sugar seed to the vibrant, tangy pellets in your hand is a testament to how much engineering is hidden inside even the simplest candies. Each step, from syrup spraying in massive tumbling pans to the delicate flavor infusion and high-speed filling lines, is executed with precision to deliver the playful, crunchy experience that has kept Nerds popular for decades. Over time, manufacturing technology for Nerds has evolved to improve efficiency and consistency. Early production relied heavily on skilled operators adjusting pans by sight and sound. Today, advanced automation systems track humidity, airflow, and syrup application rates with sensors and feedback loops, ensuring that every batch meets exacting standards. The result is a product that remains faithful to its original flavor and texture while benefiting from modern advancements in food processing equipment. There is also increasing focus on sustainability in candy production. Many factories now recover and reuse heat from syrup cooking kettles, implement water-saving cleaning systems for coating pans, and work with suppliers to source sugar from more sustainable agricultural operations. Packaging too is being reevaluated, with lighter materials and improved recyclability being considered for the future. What makes the production of Nerds especially fascinating is the balance between art and science. The process is rooted in classical confectionery techniques that date back centuries, yet it is executed on a scale and with a precision that only modern machinery can achieve. The slight variations in size and shape that give Nerds their charm are not flaws, but deliberate results of the panning process, embraced as part of their identity. The story of Twizzlers begins long before the candy reaches the factory floor. As with many mass-produced confections, the foundation is in the sourcing of high-quality raw materials. The primary ingredient is refined wheat flour, which gives Twizzlers their chewy, slightly bread-like texture. This flour arrives at the plant in bulk tanker trucks and is stored in towering silos that protect it from moisture and contaminants. From here, it is gravity-fed or pneumatically conveyed through sealed pipes to the mixing area. Alongside flour, the recipe calls for corn syrup, which provides sweetness, binding power, and flexibility, as well as sugar, which boosts flavor and adds structure. Vegetable oil, often in the form of soybean or palm oil, contributes to the mouthfeel, while food-grade colors and flavorings give Twizzlers their signature appearance and taste. Every ingredient undergoes rigorous inspection in the quality control laboratory before it can be released to production. Flour samples are checked for protein content and moisture levels. Sugar is screened for crystal uniformity, and corn syrup is tested for viscosity and purity. Liquid flavors and colors are reviewed for consistency against reference standards. Once approved, ingredients move into the blending stage, where the transformation from raw material to candy dough begins. The mixing process takes place in large stainless steel horizontal mixers fitted with heavy-duty paddles or spiral blades. The operation starts with a precise ratio of flour and sugar being combined, followed by the gradual addition of corn syrup and water. These mixers operate under controlled speeds to ensure the dough develops evenly without excessive heat buildup. Oil is incorporated next, coating the flour particles and contributing to the dough's smooth, pliable consistency. Throughout mixing, operators monitor temperature and dough texture, making small adjustments to moisture content if necessary. In many plants, this step is partially automated, with sensors tracking torque resistance in the mixer to determine when the dough has reached the ideal elasticity. Once mixed, the candy dough is transferred to the extrusion line. This is the stage where Twizzlers take on their famous twisted rope form. The dough is fed into a large extruder, essentially a high-powered screw press that forces the material through a specially designed die. The screw inside the extruder rotates at a controlled speed, kneading and pushing the dough forward while maintaining an even temperature to prevent premature setting. At the end of the barrel, the die features multiple openings shaped to produce the exact cross-section of a Twizzler rope. For the classic variety, the die includes ridged channels that create the candy's spiral grooves. As the dough emerges from the die, it is still warm and soft, making it easy to shape but vulnerable to deformation. To preserve the precise geometry, the extruded ropes immediately enter a cooling conveyor, a long belt that passes through a tunnel where chilled, dehumidified air circulates. This step lowers the candy's temperature and sets the outer surface while maintaining a chewy interior. The speed of the conveyor is carefully calibrated so that cooling is uniform along the rope's entire length. An interesting detail of Twizzlers' production is that the twist in each rope is not solely a result of the die design. The conveyor belt itself may be equipped with rollers that gently rotate the ropes as they move forward, enhancing the spiral effect. The amount of twist is a delicate balance. Too much rotation can weaken the structure and cause breakage, while too little results in a less distinctive look. After cooling, the ropes are ready to be cut to size. Cutting is performed by high-speed guillotine blades or rotary knives synchronized with the conveyor movement to avoid crushing the candy. For standard snack-sized Twizzlers, lengths are typically between 6 and 8 inches, but the same line can be adjusted to produce miniature bites or extra long versions. The cut pieces now move towards the packaging area, but before they are boxed or bagged, they undergo inspection. Quality control technicians pull samples from the line to check twist uniformity, diameter, weight, and surface texture. The moisture content is measured to ensure the candy retains its chewiness during storage. Flavor is also evaluated by trained sensory panels who compare each batch to established taste profiles. Packaging Twizzlers is a study in efficiency. Depending on the product format, they may be wrapped in flexible plastic film, placed in cardboard trays, or sealed in resealable pouches. The packaging machinery begins with an in-feed system that gently aligns the ropes into uniform stacks. These stacks are then transferred into forming tubes where the plastic film is drawn around them, sealed along the edge with heat, and cut into individual packs. Heat-sealed jaws close the ends to lock in freshness and protect the candy from moisture and oxygen. Lot codes, manufacturing dates, and product identifiers are printed directly onto the packaging by inkjet or thermal printers, ensuring traceability for every unit. Sealed packages are collected onto a takeaway conveyor and then collated into larger cartons for shipping. These cartons are stacked on pallets by robotic palletizers, which arrange the boxes in stable patterns and wrap them in stretch film to secure the load. From here, the pallets are moved to the warehouse, a temperature-controlled environment designed to maintain product quality. Although Twizzlers are relatively stable due to their low moisture and high sugar content, excessive heat can cause surface stickiness or deformation, so storage temperatures are carefully regulated. The finished products are then shipped to distribution centers, retail outlets, and export markets. Behind all of this is a network of automation systems and process controls that keep production running smoothly. Modern Twizzlers plants rely on programmable logic controllers to coordinate mixer cycles, extrusion pressures, conveyor speeds, and packaging rates. These systems integrate with quality control data, enabling operators to adjust parameters in real time if a batch shows signs of deviation from the standard. The flavoring of Twizzlers deserves special mention. While the classic strawberry variety is the most famous, the process allows for a wide range of flavors, from cherry to chocolate to licorice. In each case, the flavor oils are blended into the dough at the mixing stage to ensure even distribution. The choice of flavor affects other parameters as well. For example, chocolate varieties may require a slightly different extrusion temperature due to the fat content in cocoa powder, while licorice varieties may use molasses or anise oil that alter dough handling characteristics. Over the years, Twizzlers production has been refined not only for efficiency, but also for consistency. Early methods required more manual handling, with operators guiding ropes off the extruder and cutting them by hand. Today's operations are highly automated, with minimal direct contact between workers and the product. This not only improves hygiene, but also allows for higher output with fewer defects. Sustainability is becoming a greater focus in candy manufacturing as well. Plants are investing in closed-loop water systems for cooling conveyors, energy-efficient ovens for any heat treatment steps, and waste reduction programs that recycle off-spec candy back into the mix when feasible. Packaging materials are also being evaluated for recyclability, with thinner films and plant-based plastics under consideration. What makes the Twizzlers process so fascinating is the combination of bakery-like dough handling with candy-making sweetness. The extrusion technology is similar to that used in pasta production, yet the ingredients and post-extrusion handling are firmly rooted in confectionery science. It is a hybrid process that demands both mechanical precision and an understanding of how sugars, starches, and fats interact under heat and pressure. When you pick up a pack of Twizzlers, you are holding the result of careful ingredient selection, finely tuned mixing and extrusion, precise cooling and twisting, and airtight packaging. Each rope is the product of countless micro adjustments in speed, temperature, and formulation that ensure the candy's texture, flavor, and appearance are exactly as consumers expect. The story of a Haribo gummy begins with the ingredients, each of which is selected for quality and consistency. At the heart of the recipe is gelatin, a protein derived from collagen that gives the candy its characteristic elastic texture. This gelatin arrives at the factory in dry, granulated form and must be carefully hydrated before use. Alongside gelatin, the formulation includes glucose syrup, often produced from wheat or cornstarch, which provides body, prevents crystallization, and contributes to the chewiness. Sugar is another mainstay, giving sweetness and structural integrity. Additional ingredients include citric acid for tartness, natural and artificial flavorings for each variety, and food-safe colorants to create the rainbow of hues that define Haribo's product line. Every batch of ingredients undergoes rigorous testing in a quality control laboratory before it reaches the main production floor. Gelatin is checked for bloom strength, which determines the firmness of the finished candy. Glucose syrup is tested for solids content and viscosity, ensuring it will flow and set properly in the cooking process. Flavor and color concentrates are measured for potency and compared against established standards. Only when the raw materials pass inspection are they released to the production team. The first major step in making Haribo gummies is the cooking process. This begins in large stainless steel vessels called dissolvers or cooking kettles. Here, sugar, glucose syrup, and water are combined and heated under controlled conditions. The heating process brings the mixture to a high temperature, often in the range of 110 to 140 degrees Celsius, allowing the sugars to dissolve completely and the syrup to thicken. Once the sugar syrup reaches the correct density, pre-soaked gelatin is added. The gelatin is never boiled, as high temperatures would damage its gelling properties. Instead, it is stirred in gently once the syrup has cooled to a safe range, typically between 80 and 90 degrees Celsius. At this point, flavorings, acids, and colors are added. For gummy bears, this might include lemon, orange, raspberry, apple, and strawberry flavor profiles, each paired with a corresponding color. The additives are metered in with precision pumps to ensure every batch is consistent in both taste and appearance. Stirring must be thorough but gentle to avoid incorporating excess air bubbles, which could mar the candy's surface. Once the mixture is fully blended, it is ready to be formed into shapes. This is where Haribo's distinctive starch molding process comes into play. The company uses a method called the Mogul system, an automated production line that allows liquid candy to be deposited into detailed molds with incredible precision. The process begins with large trays filled with a fine, dry cornstarch powder. This starch serves two purposes. It prevents the sticky candy from clinging to the trays, and it helps wick away excess moisture during the setting stage. Each tray passes through a stamping unit where metal dies press the shape of the candy into the starch. Tiny, bare outlines, cola bottle profiles, or whatever form is being produced. The impressions are crisp and exact, ready to receive the warm, liquid mixture. From the cooking kettles, the candy syrup is pumped through heated pipelines to a series of depositor nozzles. These nozzles align perfectly with the starch impressions and release measured amounts of syrup into each cavity. The depositor can switch flavors and colors quickly, allowing for multiple varieties to be produced on the same line with minimal downtime. Once deposited, the trays of liquid candy are conveyed into a long climate-controlled curing room. Here, they rest for 12 to 72 hours, depending on the recipe, temperature, and humidity. During this time, the gelatin network fully sets, giving the candy its final chewy texture, while the starch continues to absorb surface moisture. The curing rooms are kept at specific humidity levels to prevent the candies from drying out too much or becoming sticky. When curing is complete, the trays move to the demolding stage. The gummy shapes are gently lifted from the starch, which is recovered, dried, and sieved for reuse in future molding. Any excess starch clinging to the candies is removed through a combination of mechanical shaking and soft air jets. The gummies, now fully formed, have a matte appearance and a slightly tacky feel at this stage. To give them the glossy finish consumers recognize, the candies are transferred to large rotating drums called glazing pans. Inside, they are tumbled with a thin coating of food-grade waxes such as carnauba or beeswax, along with oils that enhance shine and prevent sticking. The glazing process is quick but crucial, as it also provides a protective barrier against moisture changes during storage. With their appearance perfected, the gummies proceed to the packaging area. Here, high-speed conveyors feed them into multi-head weighers, machines equipped with multiple hoppers that dispense exact amounts to achieve the target package weight. The candies are dropped into pre-formed bags or into the forming tubes of vertical form-fill-seal machines. These machines create a bag from a continuous roll of printed film. Seal the bottom, fill it with the candy, then seal the top in one continuous motion. For variety packs, sophisticated sorting systems group different gummy shapes and flavors in precise ratios before they reach the weighing step. This ensures that every bag contains the intended assortment. Packaging films are chosen for their barrier properties, keeping the gummies fresh while displaying bright branding. Each bag receives a lot code and best before date for traceability, then passes through metal detection equipment as a final safety measure. The finished bags are gathered into cartons, stacked onto pallets, and wrapped in stretch film to stabilize them for shipping. Pallets are moved to temperature-controlled storage areas until they are loaded onto trucks bound for distribution centers and retailers around the world. Throughout the entire process, quality control remains a constant presence. Samples from each batch are taken at multiple points, from syrup cooking to molding, curing, and packaging, to ensure that every aspect meets Haribo's specifications. Technicians test texture with penetrometers to confirm the perfect chew, measure pH to monitor acidity, and use colorimeters to verify hue accuracy. Flavor panels taste test samples to ensure the product matches established sensory profiles. The production of Haribo gummies has evolved significantly over the decades. Early batches were made by hand in small copper kettles and poured into starch molds one tray at a time. Today's lines can produce hundreds of thousands of pieces per hour, with computerized systems controlling every variable. Yet the core principles remain the same: quality ingredients, precise cooking, careful molding, and patient curing. There is also a growing emphasis on sustainability within Haribo's operations. Many plants now use energy recovery systems to capture heat from cooking processes, recycle starch indefinitely, and source gelatin and sugar from more sustainable supply chains. Efforts to reduce packaging weight and increase recyclability are also underway, ensuring that the joy of gummy bears has a smaller environmental footprint. What makes Haribo's process fascinating is the blend of old-world confectionery craftsmanship and high-tech automation. The mogul molding system, for instance, is an industry standard, yet it still relies on principles that candy makers have used for over a century. The long curing time is a reminder that some aspects of candy making simply cannot be rushed if the desired texture is to be achieved. By the time a bag of Haribo gummies reaches the shelf, it has undergone a transformation from raw sugar, syrup, and gelatin into a perfectly shaped, flavorful, and brightly colored treat. Behind each piece is a network of ingredient sourcing, controlled cooking, precision molding, and patient curing, all supported by layers of quality control and packaging expertise. Chocolate begins its life not in the factory, but on the tropical cacao farms that line the equator. These farms are located in countries across West Africa, Central and South America, and Southeast Asia, with Ivory Coast and Ghana among the world's top producers. The climate in these regions, hot, humid, and with rich, well-draining soil, is essential for the cultivation of Theobroma cacao, the tree that produces cacao pods. Each pod contains 20 to 50 seeds, known as cacao beans, surrounded by a sweet, pulpy, white fruit. These beans are the raw foundation of all chocolate products. The cacao harvest is entirely manual. Farmers use machetes or curved knives attached to long poles to carefully cut ripe pods from the trees without damaging the branches. A single mature tree may produce between 20 and 30 pods per year, and since cacao does not ripen all at once, harvesting occurs continuously over several months. Once harvested, the pods are collected in piles and opened by hand using machetes. The beans, still coated in sticky white pulp, are scooped out and prepared for fermentation, the first transformative step in the chocolate making process. Fermentation typically occurs on the farm or at centralized collection centers. Though it might sound like a simple resting period, fermentation is a critical and highly sensitive step that chemically alters the beans and begins to develop the flavor precursors of chocolate. Beans are placed in shallow, slatted wooden boxes or piled into heaps and covered with banana leaves. This environment encourages the growth of natural yeasts and bacteria that convert sugars in the pulp into alcohol and acids. As the temperature rises, often reaching 45 to 50 degrees Celsius, the bean's internal structure changes. Enzymes are activated, cell walls are broken down, and bitter polyphenols begin to transform into the complex flavor compounds that will later give chocolate its signature taste. Fermentation typically lasts 5 to 7 days, during which the beans are turned or mixed once or twice a day to ensure even microbial activity and oxygenation. This step is closely monitored, as under-fermentation leads to bland or vegetal flavors, while over-fermentation can introduce off notes like mold, vinegar, or excessive bitterness. Many large chocolate manufacturers, even though they don't ferment beans on site, have established quality programs with their cacao suppliers, training them in fermentation control, and even requiring on-site testing of pH and temperature during the process. Once fermentation is complete, the beans are spread out to dry. Drying can be done on large tarpaulins, bamboo mats, or raised wooden platforms under the sun. Industrial cacao processors often prefer sun drying, which can take 5 to 10 days, as it produces cleaner, more natural flavor profiles. During drying, the beans are turned regularly to ensure even moisture loss. The goal is to reduce the moisture content to around 6%, 7%, a safe level that prevents mold and microbial growth during storage and transport. At this point, the beans are still covered in their thin, brittle shells and have taken on a dark brown color, with their signature earthy, chocolatey aroma starting to develop. The beans are carefully bagged in burlap sacks, usually 60 to 65 kilograms per bag, and labeled with origin information including country, region, farm or co-op, and processing dates. These bags are then consolidated for export. Exporting cacao beans requires extreme care and logistics planning. Moisture, heat, and exposure to foreign odors can degrade the beans before they even reach the factory. To prevent spoilage, the sacks are loaded into dry, ventilated shipping containers, often lined with insulating material or desiccant packs to control humidity. During long overseas shipments, particularly by sea freight, the cargo is monitored using data loggers that track temperature and humidity. If the beans are exposed to extreme conditions, entire shipments can be rejected by the receiving chocolate manufacturer. When the beans arrive at the chocolate factory, usually located in Europe, North America, or Asia, they undergo a rigorous intake and inspection process. This is where industrial chocolate production truly begins. First, the bags are unloaded into a receiving area, where samples are drawn from each lot and taken to the quality control lab. Here, technicians measure moisture content, check for mold or insect damage, and grade the beans based on size, color, and cut tests. cut test involves slicing a sample of beans lengthwise and examining the cross-section. Properly fermented beans will have a uniform, slightly purplish interior with no signs of germination or off colors. Beans that meet the manufacturer's standards are then approved for processing. The sacks are emptied into large hoppers that feed the cleaning and pre-processing line. At this point, the factory begins to function much like a grain mill, sorting, cleaning, and prepping the raw material for transformation. The first stage is mechanical cleaning. The beans pass through vibrating screens and air jets that remove sticks, stones, dust, string, and other foreign materials. Magnetic separators remove any stray metal particles picked up during harvest or shipping. After cleaning, the beans are often sorted by size. This is an optional step, but many high-end chocolate makers insist on sorting to ensure that beans of uniform size are roasted together. Uneven roasting is a major risk if large and small beans are mixed, as the small beans may burn while the larger ones under-roast. Before roasting, the factory may also conduct a dehumidification step, particularly if the beans arrived slightly above target moisture. Large rotary dryers or low-temperature ovens are used to bring the beans into precise moisture range, often 5%, 6%, to prepare for optimal roast conditions. This is all monitored through programmable logic controllers that track time, temperature, airflow rate, and moisture loss in real time. With the cacao beans now thoroughly cleaned, dried to precise moisture levels, sorted by size, and passed through rigorous quality inspections, the chocolate production process enters one of its most transformative and delicate phases: roasting. This step marks the moment when raw agricultural product begins to develop the hallmark sensory properties of finished chocolate: aroma, depth, bitterness, sweetness, and complexity. Far from being a simple baking process, industrial chocolate roasting is a finely tuned science that must balance heat, time, air circulation, and even bean origin to unlock the flavor potential locked within the bean's cellular structure. The roasted profile of chocolate is not one size fits all. It varies greatly depending on the origin of the beans, the desired flavor profile of the final product, and the style of chocolate being produced, whether it's milk, dark, or even single origin specialty bars. As such, chocolate factories have roasting protocols tailored to each bean variety and product type. These protocols are logged as roast profiles, charts that map temperature over time, often broken into phases: drying, browning, and development. Each phase requires precise thermal input and airflow to extract the right flavors without burning or flattening the bean. Industrial chocolate factories use several types of roasters depending on scale and product goals. The most common are batch drum roasters and continuous roasters. Batch drum roasters, similar in design to coffee roasters but much larger, feature a rotating cylindrical drum made from stainless steel. Beans are loaded into the drum, which rotates over direct or indirect heat, with hot air circulated through the drum chamber. Temperature sensors embedded in the drum monitor the bean mass, ambient air, and exhaust temperatures simultaneously. Factory operators can adjust drum speed, airflow rate, and burner intensity through PLC-controlled interfaces to manage the roast curve. Roasting typically begins at a lower temperature, around 100 degrees Celsius, to drive off any remaining surface moisture. This is the drying phase and usually lasts for 5 to 10 minutes. The beans then enter the browning phase, where the Maillard reaction begins. This is the chemical process that causes amino acids and reducing sugars in the beans to recombine and form hundreds of flavor compounds: nutty, roasted, caramelized, and acidic notes that are essential for chocolate's complexity. This phase is carefully controlled, usually taking another 10 to 15 minutes, with bean temperatures rising to 120-140 degrees Celsius. The final stage of roasting is known as development, or the finishing phase. Here, the beans are brought to their final internal temperature, typically between 135 degrees Celsius and 150 degrees Celsius, depending on the desired flavor profile. This phase is brief, often just 2 to 5 minutes, but it's critically important. Too little development, and the flavor may be grassy or underwhelming. Too much, and the chocolate may taste burnt, acrid, or flat. Advanced factories use real-time infrared cameras and bean temperature probes to monitor this phase with incredible accuracy, sometimes recording temperatures at 1-second intervals. After roasting, the beans must be cooled quickly to halt the cooking process. This is usually achieved in a dedicated cooling drum or tray system, where ambient or chilled air is blown across the beans using high-speed fans. Cooling not only stops the roast, but it also firms up the bean shell and prevents steam buildup, which could cause condensation or spoilage during storage. At this point, the beans are dark brown, fragrant, and brittle, but they still contain their outer shells, a thin, papery husk that must be removed to access the valuable interior, the cacao nib. The next phase is known as winnowing. Winnowing is a mechanical process that cracks the beans open and separates the lightweight shells from the dense nibs using a combination of crushing and air classification. In a large-scale chocolate factory, beans are first passed through a pre-cracker or roll crusher, which breaks them into fragments of varying size. The cracked mixture is then fed into a winnowing chamber, often a series of vertical air columns or vibrating conveyor belts, where calibrated air jets or suction systems separate the heavier nibs from the lighter shells. The airflow is precisely tuned so that the nibs fall to the bottom collection bins while the husks are drawn upward into separate waste hoppers. The result is a batch of pure cacao nibs, dark, rich, and packed with flavor and cocoa solids. These nibs are now ready to be transformed into chocolate liquor, not an alcoholic beverage, but a thick, paste-like substance made from finely ground cacao nibs. This is where the chocolate truly begins to take shape. To produce liquor, the nibs are passed through industrial grinders known as pre-refiners or impact mills. These machines use either rotating steel blades or stone rollers to shear the nibs into smaller and smaller particles. As the nibs are ground, frictional heat causes the cocoa butter inside to melt. This transforms the mixture from a coarse, gritty powder into a flowing paste with a smooth, velvety texture. The grinding process typically reduces particle size to around 80 to 100 microns during this first stage. From here, the liquor is either held in heated tanks for further processing or sent directly to the next grinding phase, refining. Refining is the step where particle size is further reduced to achieve the smooth mouthfeel expected from high-quality chocolate. This is performed using 5-roll refiners or ball mills. 5-roll refiners consist of 5 horizontally stacked steel rollers, each rotating at a different speed. The chocolate liquor is fed into the gap between the rollers, which progressively shear the particles down to between 15 and 25 microns. At this size, individual cocoa and sugar particles are too small for the tongue to detect, giving chocolate its creamy texture. In factories producing sweetened chocolate, sugar is added during this refining phase. The sugar, already pre-milled to ensure consistent granule size, is blended with the chocolate liquor to form what's called a chocolate crumb. Depending on the recipe, milk powder, vanilla, lecithin, and other ingredients may also be added at this stage. These additions are carefully weighed and dosed using automated batching systems, which ensure that every batch conforms to a master formulation. After refining, the chocolate mass still feels dry and powdery. To turn it into a cohesive, pourable liquid with a smooth finish and stable flavor, it must undergo conching, a prolonged mixing and aeration process that can last anywhere from several hours to multiple days. Conching takes place in large heated vessels fitted with rotary arms or heavy granite rollers. The goal of conching is threefold: to develop flavor by oxidizing volatile acids, to smooth texture by distributing fat uniformly, and to improve viscosity by reducing moisture and undesirable compounds. The conching process is controlled in phases: dry conching, where the paste is crumbly and thick; plastic conching, where it softens and flows; and liquid conching, where the mass becomes fully fluid. Each conching profile is custom tailored to the specific chocolate type being produced. Milk chocolate, for instance, requires longer conching to balance milk solids and sugars, while high percentage dark chocolate may be conched shorter to retain more of its natural acidity and origin flavor. Throughout conching, temperature, shear force, and oxygen flow are all regulated. Some factories utilize closed-loop conches with nitrogen blanketing to reduce oxidation, while others incorporate vacuum systems to pull out undesirable volatile compounds. This stage is monitored using inline viscometers and gas sensors, ensuring consistent output from batch to batch. At this point in the process, the chocolate mixture has reached a smooth, glossy, and richly aromatic state. It flows as a thick liquid, its flavors matured and balanced from hours of careful mixing, grinding, and aeration. The next phase transforms that liquid mass into a finished, stable form suitable for packaging and distribution. This involves cooling and crystallizing the cocoa butter within the mixture in a very specific way, a stage that requires precision and control over time, temperature, and movement. The goal here is to encourage the formation of the right type of crystal structure in the cocoa butter. Cocoa butter can solidify into several different crystalline forms, but only one of them results in a final product that has a smooth surface, sharp snap, resistance to melting in the hand, and a stable shelf life. To achieve this, the entire mass must be carefully tempered. Tempering is carried out in machines built for continuous flow and temperature control. These tempering units begin by first heating the mixture slightly above the melting point of all crystal forms, typically around 45 degrees Celsius. This ensures that any existing crystal structures are completely melted away. The liquid is then cooled gradually, usually to somewhere between 26 degrees Celsius and 28 degrees Celsius, depending on the specific type being produced. During this cooling, movement is maintained through stirring blades and flow channels, allowing the desired type of stable crystal to begin forming. Once enough of these seeds have developed, the mixture is gently reheated to a precise finishing temperature, usually just under 32 degrees Celsius. This final temperature is critical. It allows the seeded crystals to remain while eliminating the unstable forms that would cause bloom or textural issues later on. The flow, agitation, and temperature must be maintained within a very tight range. Modern tempering equipment uses inline sensors and feedback control loops to monitor these values in real time, ensuring the product is correctly tempered before it moves into the next station. From here, the tempered liquid is conveyed to the molding lines. These are high-speed, fully automated systems designed to pour precise volumes into molds of various sizes and shapes. The molds themselves are preheated slightly to prevent premature setting and ensure even flow. As the mixture is deposited into each cavity, vibratory tables shake the molds to remove any trapped air bubbles and ensure a perfectly even distribution. Once filled and vibrated, the molds are sent through long cooling tunnels. These enclosed, refrigerated belt systems gradually reduce the temperature in controlled stages, allowing the internal structure to set without cracking or warping. The airflow, tunnel speed, and humidity are all precisely calibrated to avoid moisture condensation on the surface, which could lead to dull or sticky finishes. Once cooled and fully solidified, the bars or shapes are released from the molds using a combination of mechanical pushes and short bursts of air. The finished items are then transferred onto conveyors that lead to the inspection zone. Here, Vision systems scan each piece for defects, looking for uneven surfaces, cracks, color inconsistency, or any signs of bloom. Imperfect units are automatically ejected from the line for recycling. In many operations, these rejected items are remelted and retempered to be used again in the next batch. From this point, the finished product moves toward wrapping and packaging. The type of packaging depends on the product format, whether individual bars, boxed assortments, filled shapes, or bulk items for further processing. For single bars, wrapping lines are designed to handle high volumes per minute. Each bar is conveyed through a wrapping machine that cuts, folds, and heat seals the wrapper with high-speed precision. These machines are synchronized with the flow of the production line to prevent jamming, tearing, or misalignment. Packaging materials include metallized films, waxed paper, biodegradable foils, or composite laminates. These materials are selected based on the storage requirements of the product, the region's environmental regulations, and the shelf life goals. Many manufacturers also include oxygen scavengers or modified atmosphere sealing to enhance freshness, especially for filled products. After wrapping, individual bars or pieces are grouped into larger cartons or boxes by pick-and-place robotics. These machines identify product orientation, pick them up using suction or mechanical fingers, and place them into retail boxes, display trays, or bulk cases. The outer cartons are sealed, labeled, and pass through final quality control scanners that confirm weight, barcode accuracy, and expiration coding. Palletizing comes next. Stacked and secured cartons are placed onto shipping pallets according to loading patterns that maximize space efficiency and minimize stress on the bottom layers. Pallets are shrink wrapped using rotating arms or heat tunnels and then labeled with shipping codes, batch numbers, and destination data. The entire production record for each batch is digitally logged in the factory's quality control database. This includes source information for the raw ingredients, roasting and grinding parameters, conching durations, tempering temperatures, molding timestamps, and final inspection results. Should any issue arise downstream in distribution or retail, the system allows full traceability back to the moment each unit was created. Finished pallets are moved to climate-controlled storage zones. These warehouse areas are kept at stable temperatures, generally between 16 degrees Celsius and 20 degrees Celsius, to prevent melting, blooming, or flavor degradation. Humidity is also controlled, often under 60%, to protect the product and packaging integrity. Some products are stored under specific lighting conditions to prevent discoloration, particularly white and milk varieties that are more sensitive to UV exposure. Finally, shipments are released according to production schedules aligned with distribution needs. Orders are grouped by destination region, retailer, or distributor and loaded into trucks, shipping containers, or cargo planes. Temperature data loggers may be placed inside shipments to confirm that climate conditions remain within acceptable limits throughout transport. Though the product has now left the facility, its connection to the factory process is never lost. Retail complaints, test results, or customer feedback can all be traced back to the specific day, shift, and equipment used. Manufacturers regularly run shelf life simulations, flavor degradation tests, and mechanical stress analyses on packaged goods to validate the effectiveness of the process long after the final product leaves the line. Every stage, from raw bean to packaged bar, is designed not just for efficiency, but for repeatability and control. Factories producing chocolate operate like laboratories with strict protocols, while still honoring the craft behind each ingredient's transformation. This combination of technical discipline and sensory artistry is what makes industrial chocolate manufacturing one of the most exacting and fascinating operations in the global food industry. Once the finished chocolate leaves the factory, perfectly tempered, molded, cooled, and sealed in its final packaging, the industrial process doesn't come to a halt. a crucial final phase still unfolds, one that ensures the product not only reaches shelves in perfect condition, but also maintains its quality and integrity through transportation, storage, retail display, and eventual consumption. This extended phase is managed through sophisticated logistics, environmental monitoring, supply chain coordination, and continuous quality assurance practices. While this may seem like the back end of production, it is deeply integrated into how chocolate is made and maintained on a global scale. Immediately after production, the packaged chocolate is transferred into climate-controlled storage areas within the factory's distribution wing. These areas are tightly regulated to prevent degradation. The ideal temperature for storing finished chocolate is generally between 16 degrees Celsius and 20 degrees Celsius, with humidity kept below 60%. Above this humidity threshold, there is risk of sugar bloom, a white, dusty coating that forms when moisture causes sugar to dissolve and then recrystallize on the surface. Below this range, especially in dry climates, static electricity and brittleness can become issues, particularly for filled or aerated varieties. Storage racks are arranged to allow airflow between pallets. Each pallet is tagged with a unique identifier and scanned into the warehouse management system. This allows the system to track not only where each batch is physically stored, but also how long it's been in inventory, where it needs to go next, and whether it's awaiting any last-minute quality hold releases. Before a batch can ship, a final set of post-production tests is sometimes performed on a sample group. These tests may include accelerated shelf life simulations, where chocolate is exposed to varying environmental conditions in climate chambers to determine how it performs over time. Texture analyzers may test for brittleness or softening, while gas chromatography may be used to check whether volatile flavor compounds remain stable. Once cleared, shipments are scheduled for distribution, whether headed to a supermarket distribution center, a specialty retailer, or international export. The chocolate must be loaded into transport systems that preserve the exacting conditions it was stored under. This can involve refrigerated or climate-controlled trailers, especially for higher-end varieties or filled products that are more vulnerable to heat. During warmer seasons, some companies delay shipments until nightfall or equip their pallets with insulation wraps to preserve temperature during brief exposure windows. Transport vehicles are often equipped with onboard temperature loggers. These small, battery-powered devices record environmental conditions every few minutes and are reviewed upon delivery to confirm that there were no unacceptable spikes in heat or humidity. If the data shows a breach, the receiving party may reject the shipment, even if the exterior packaging appears untouched. This level of accountability ensures that the integrity of the product is never assumed, but always confirmed. At the retailer level, chocolate continues to face environmental risks. Supermarkets and convenience stores may place chocolate in non-refrigerated aisles where exposure to lighting, fluctuating temperatures, and air conditioning vents can impact quality. To mitigate this, factory teams sometimes conduct in-store audits, either directly or through contracted merchandising specialists. These audits include checks on product placement, shelf temperature, rotation practices, and visible quality. Manufacturers also perform pull tests, where random samples are purchased directly from stores and sent back to internal labs for analysis. This helps determine if the product maintains its texture, snap, and flavor after weeks or months in the distribution system. These real-world results are fed back into the production process, helping engineers refine shelf life goals, tweak packaging barrier specifications, or adjust emulsifier ratios for better thermal resilience. Despite this rigorous system, the industrial process isn't rigid. Many manufacturers now build flexibility into their operations to support seasonal releases, new flavor experiments, and evolving consumer preferences. This includes small batch production lines within large factories that can produce limited runs of new recipes without interrupting mass-scale output. Even with these small lines, all the same steps: roasting, refining, conching, tempering, molding, wrapping, are followed precisely, but in more agile formats. The long arc of chocolate production, from tropical farm to factory and beyond, is a story of transformation, precision, and protection. Each stage is critical, from developing flavor precursors during fermentation, to unlocking complexity through roasting, to achieving that final, glossy finish through proper tempering and cooling. It's not just about creating a product, it's about preserving it, tracking it, testing it, and delivering it across continents in exactly the state it was intended. The journey begins with sourcing green coffee beans. Factories procure these beans in large quantities from coffee-growing regions such as Brazil, Colombia, Vietnam, and Ethiopia. Since instant coffee requires consistent flavor profiles, manufacturers often blend beans from various regions to create a balanced and standardized flavor. Upon arrival at the factory, the green coffee beans are subjected to rigorous quality control checks. Samples are tested for size, moisture content, and defects to ensure the beans meet the factory's standards for processing. Once approved, the beans are stored in massive silos made of food-grade stainless steel or aluminum to protect them from contamination, pests, and humidity. These silos are equipped with automated systems that precisely dispense beans onto the production line. The first major step in processing the beans is cleaning. Coffee beans, even after being cleaned at their origin, may still contain impurities such as dirt, stones, sticks, or metal fragments. In the factory, the cleaning process involves several stages. Vibrating screens sift the beans to remove large debris, while air classifiers blow away lighter materials like husks or dust. Magnets are used to extract any metallic particles. Some factories also employ optical sorting machines, which use cameras and sensors to identify and remove defective beans or foreign objects. This thorough cleaning ensures that only high-quality beans proceed to the roasting stage. Roasting is a critical step in developing the rich, complex flavors of coffee. Factories use industrial coffee roasters, which can process thousands of pounds of beans per hour. The roasting process is controlled by highly advanced systems that allow operators to customize the roast profile for specific flavor outcomes. For instant coffee, medium to dark roasts are commonly used, as they bring out bold flavors that translate well into the final soluble product. Roasting temperatures typically range between 370 and 540 degrees Fahrenheit, depending on the desired flavor profile. During roasting, the beans undergo the Maillard reaction, a chemical process that creates the characteristic aromas and flavors of coffee. The roasting equipment includes temperature sensors and real-time monitoring systems to ensure uniform roasting across large batches. Once the roasting is complete, the beans are cooled rapidly to stop the roasting process and prevent overcooking. Factories use air cooling systems or water spray cooling, depending on the setup. Cooling is an important step, as improperly cooled beans can lose their flavor or become brittle. After cooling, the beans are sent to grinding machines. The grinding stage reduces the roasted coffee beans into smaller particles, which will be used for the brewing process. Factories use industrial grinders, such as roller mills or hammer mills, capable of producing a consistent grind size. The grind size is crucial because it affects the extraction process that follows. For instant coffee, a relatively coarse grind is typically used to optimize the brewing process in the factory. The ground coffee is then stored in intermediate holding bins, where it is kept fresh until it is ready to be brewed. Brewing is the next major step in instant coffee production, and it is carried out on an industrial scale. Massive brewing systems, similar to oversized percolators, are used to extract the soluble compounds from the ground coffee. These systems consist of large stainless steel extraction tanks or columns, which are designed to hold thousands of gallons of water and coffee grounds. Hot water is circulated through the coffee grounds at precise temperatures and pressures, mimicking the brewing process used at home, but on a much larger scale. Typically, water temperatures range between 190 and 205 degrees Fahrenheit, and the brewing time is carefully controlled to maximize flavor extraction while minimizing bitterness. The brewed coffee concentrate, a liquid containing the extracted soluble compounds, is then filtered to remove the spent coffee grounds. Factories use advanced filtration systems, such as centrifugal separators or fine mesh filters, to ensure that no solid particles remain in the liquid. The spent grounds are often dried and repurposed as fertilizer or biomass fuel, making use of every part of the raw material. At this stage, the coffee concentrate is a highly aromatic liquid, but it is still far from the final product. The challenge is to transform this liquid concentrate into a stable, dry, and soluble form. Factories use one of two main methods for this: spray drying or freeze drying. Spray drying is a fast and cost-effective method that is commonly used to produce instant coffee powder. The coffee concentrate is first preheated to reduce its moisture content. It is then pumped into a tall, spray drying chamber equipped with nozzles that disperse the liquid into fine droplets. At the same time, hot air, typically around 480 degrees Fahrenheit, is blown into the chamber. As the droplets fall through the chamber, the water in the coffee concentrate rapidly evaporates, leaving behind fine coffee powder. Spray drying is efficient and capable of processing large volumes, but the high temperatures can sometimes lead to a slight loss of flavor and aroma. Freeze drying, on the other hand, is a more delicate and sophisticated process that better preserves the natural flavors and aromas of coffee. The coffee concentrate is first frozen at extremely low temperatures, usually around 40 degrees Fahrenheit, to form solid slabs or granules. These frozen coffee pieces are then placed in a vacuum chamber. Inside the chamber, the frozen water in the coffee undergoes sublimation, a process where ice turns directly into vapor without passing through the liquid phase. This method requires precise control of temperature and pressure and takes longer than spray drying, but it produces high-quality granules of instant coffee that dissolve easily in water. After the drying process, the instant coffee is sifted and graded by particle size to ensure uniformity. Any oversized or undersized particles are removed, and the coffee is blended to create a consistent final product. Factories conduct rigorous quality control tests at this stage, including flavor analysis, solubility testing, and moisture content measurement. These tests ensure that the instant coffee meets the desired standards for flavor, aroma, and texture. Packaging is the final step in the production process, and it is designed to protect the coffee from moisture and preserve its freshness. The dried instant coffee is transported to high-speed filling machines, which dispense precise amounts of coffee into jars, tins, or pouches. Factories use nitrogen flushing systems to replace oxygen in the packaging, as oxygen can degrade the coffee over time. The jars are sealed with airtight lids, while pouches are heat sealed to maintain freshness. After sealing, the packages move to labeling stations, where automated systems apply branding, ingredient lists, and expiration dates. Each package undergoes a final inspection using vision systems to ensure there are no defects in the seals or labels. Once approved, the packages are packed into cartons or cases using robotic packing systems and prepared for shipping. Pallets of instant coffee are stacked and wrapped for stability before being loaded onto trucks or containers for global distribution. Throughout the entire process, factories rely on advanced automation and engineering to ensure efficiency and consistency. Programmable logic controllers and supervisory control and data acquisition systems monitor and control every stage of production, from roasting and brewing to drying and packaging. Real-time data on temperature, pressure, humidity, and other parameters allows operators to make precise adjustments as needed, minimizing waste and ensuring high-quality output. Hygiene and food safety are also paramount in instant coffee production. Production areas are designed with food-grade stainless steel surfaces, seamless flooring, and clean room environments to prevent contamination. Positive air pressure systems are used to keep airborne particles out of critical areas, and employees are required to follow strict hygiene protocols, including wearing protective clothing and adhering to cleaning schedules. Factories are regularly inspected and certified to meet international food safety standards. Inside a tea factory, the transformation of fresh tea leaves into the familiar tea bags, loose leaf tea, or powdered varieties is a carefully orchestrated process. It is a seamless blend of tradition, precision engineering, and science. Every step of the way, from leaf intake to packaging, is designed to preserve the flavor, aroma, and quality that tea enthusiasts have come to expect. While the type of tea being produced, whether black, green, oolong, or white, dictates specific steps in the process, the overall journey is one of meticulous attention to detail, where both manual expertise and advanced machinery play vital roles. The process begins at the tea gardens, where leaves from the Camellia sinensis plant are plucked at peak quality. For most teas, workers handpick only the top 2 leaves and a bud from each branch, as these tender parts of the plant produce the best flavor and aroma. After harvesting, the leaves are transported to the factory as quickly as possible to prevent spoilage or fermentation during transit. Many tea factories are strategically located near plantations to minimize delays and ensure freshness. Upon arrival at the factory, the tea leaves are weighed and inspected for quality. Modern tea factories are equipped with automated intake systems that separate leaves from debris such as twigs or foreign matter. Vibrating conveyor belts or mechanical sieves are commonly used at this stage to remove unwanted materials. For higher grade teas, additional manual inspections may be carried out to ensure only the finest leaves proceed to the next step. The fresh leaves are then carefully spread out in thin layers on large trays or conveyor belts, marking the beginning of the first stage in tea processing. Withering. Withering is a critical step in tea production, as it reduces the moisture content of the fresh tea leaves and prepares them for the subsequent stages of processing. In the factory, withering is typically carried out in withering troughs, long, shallow trays equipped with a system of fans and controlled airflow. Fresh tea leaves are laid out on these trays, and air is circulated over them for several hours to slowly remove moisture. For black tea, withering may last anywhere from 12 to 18 hours, while green tea requires a shorter withering time, as it needs to retain more of its fresh, grassy flavor. Temperature and humidity are carefully controlled using automated climate systems to ensure consistent results. During this stage, the leaves become softer and more pliable, making them ready for rolling. The next stage is rolling, where the tea leaves are twisted and shaped to release their essential oils and initiate oxidation if required, as with black and oolong teas. Factories use large mechanical rolling machines equipped with heavy, grooved plates or rollers. These machines apply pressure to the leaves, breaking down their cell walls and releasing their natural juices. The released juices react with oxygen in the air, beginning the oxidation process that gives black tea its characteristic flavor and color. Rolling machines can be adjusted to produce different shapes and textures, depending on the type of tea being made. For example, green teas may be rolled into tight pellets for varieties like gunpowder tea, while black teas are often left in long, wiry shapes. At this point, the production process diverges depending on the type of tea being manufactured. For black tea, oxidation is the next key step. Oxidation often mistakenly referred to as fermentation, is a chemical process that darkens the tea leaves and develops the rich, robust flavors associated with black tea. In factories, oxidation typically takes place in large, temperature-controlled rooms, where rolled tea leaves are spread out on trays or conveyor belts. These rooms maintain a controlled environment with high humidity and a temperature of around 77 to 86 degrees Fahrenheit. The leaves are periodically monitored to ensure they achieve the desired level of oxidation, which can take anywhere from 30 minutes to several hours, depending on the tea. As the leaves oxidize, they turn from green to a reddish-brown color, releasing the aromatic compounds that define black tea. In contrast, for green tea production, oxidation is intentionally prevented. To preserve the vibrant green color and fresh vegetal flavor of the leaves, factories employ a process called fixation, also known as kill green. This step involves heating the leaves immediately after rolling to deactivate the enzymes that cause oxidation. Factories use either steam or dry heat for this purpose. For Japanese-style green teas, like sencha, the leaves are steamed in specialized machines, while Chinese-style green teas are often pan-fried in large heated woks or rotating drum roasters. Fixation requires precise temperature control, as overheating can burn the leaves and underheating can fail to stop oxidation completely. Once oxidation or fixation is complete, the next step is drying, which reduces the moisture content of the tea to make it shelf stable. Drying is typically carried out in large industrial dryers or ovens equipped with temperature controls and airflow systems. Conveyor belt dryers, in which the leaves are gradually moved through a heated chamber, are common in large-scale tea factories. The temperature during drying ranges from 194 to 248 degrees Fahrenheit, depending on the type of tea and the desired final moisture content, which is usually around 3 to 5%. This step is crucial for locking in the flavor and aroma of the tea while ensuring it will not spoil during storage. After drying, the tea leaves are sorted and graded. In the sorting process, leaves are separated by size, shape, and quality using a combination of vibrating sieves, air separators, and optical sorting machines. Whole leaves, broken leaves, and small particles are separated into different grades, which are used for various tea products. For instance, whole leaves are often reserved for premium loose-leaf teas, while smaller particles are used for tea bags. Some factories also employ advanced laser sorting machines that can detect and remove any remaining foreign objects or off-spec leaves. Blending is another key step in tea production, especially for brands that aim to create consistent flavor profiles. Many teas are blended by mixing leaves from different regions, harvests, or even types of tea. Blending is carried out in large rotating drums or mixing machines, where precise quantities of different teas are combined to achieve the desired flavor. For flavored teas, additional ingredients such as dried fruit pieces, herbs, or essential oils are added during this stage. For example, Earl Grey tea is made by blending black tea leaves with bergamot oil, while chai blends often include spices like cinnamon, cardamom, and cloves. Once the tea has been blended and sorted, it is ready for packaging. Packaging is a highly automated process in modern tea factories. For loose-leaf tea, the leaves are weighed and sealed in airtight bags, tins, or foil-lined pouches to preserve freshness. For tea bags, the leaves are measured and packed into filter paper, which is then cut and sealed into individual tea bags using high-speed machines. Many factories also produce pyramid-shaped tea bags, which allow for larger leaves and better infusion. After filling, the tea bags are placed into cartons or boxes, which are sealed and labeled with branding, lot numbers, and expiration dates. Throughout the entire process, quality control plays a vital role in ensuring the tea meets rigorous standards. Factories employ trained tea tasters who sampled the tea at various stages of production to assess its flavor, aroma, and appearance. Advanced laboratory equipment is also used to measure moisture content, microbial activity, and other parameters that affect the quality and safety of the final product. Additionally, factories must comply with food safety regulations and certifications, such as ISO 22000 or HACCP, to ensure their tea is safe for consumption. Cocoa powder, the cornerstone of countless recipes from rich chocolate cakes to creamy hot cocoa, is the product of a complex and fascinating manufacturing process that combines agricultural expertise with advanced industrial engineering. Behind every tin or packet of cocoa powder lies a detailed, multi-step operation where raw cacao beans are transformed into the fine, flavorful powder that has become a staple ingredient in kitchens around the world. This process begins on cacao farms and culminates in a factory where specialized equipment and precise techniques ensure the consistency, flavor, and quality of the finished product. Let's take an in-depth journey into how cocoa powder is made, exploring each stage of the process, from bean to powder. The story of cocoa powder begins with the cacao tree, which thrives in tropical regions near the equator, such as West Africa, Southeast Asia, and Central and South America. The cacao tree produces pods that contain cacao beans surrounded by a sweet, sticky pulp. These beans are the raw material for cocoa powder. Once harvested, the pods are split open to extract the beans, which are then immediately subjected to the first critical step in the process: fermentation. Fermentation is a natural and essential process that develops the flavor precursors in cacao beans. After being removed from the pods, the beans and their surrounding pulp are placed into shallow wooden boxes or large banana leaf-lined baskets, where they ferment over a period of 5 to 7 days. During this time, natural yeasts and bacteria break down the sugars in the pulp, generating heat and causing the temperature in the fermentation pile to rise significantly, often reaching over 120 degrees Fahrenheit. This heat triggers a series of chemical reactions within the beans, developing their characteristic chocolate flavor while reducing bitterness. The beans are turned periodically to ensure even fermentation and prevent spoilage. Once fermentation is complete, the beans are removed from the boxes or baskets and sent to the next stage: drying. Drying is critical for stabilizing the fermented beans and reducing their moisture content to a level suitable for storage and transport. Traditionally, cacao beans are dried under the sun, spread out in thin layers on large drying racks or patios, and turned regularly with wooden rakes to ensure even drying. In modern cocoa production, factories may use mechanical dryers when weather conditions are unsuitable for sun drying or to speed up the process. These machines blow heated air over the beans to achieve the target moisture content, which is usually around 6 to 7%. Proper drying is essential because any excess moisture could lead to mold growth during storage or shipping. Once dried, the beans are sorted, graded, and packed into jute bags or bulk containers, ready for shipment to processing facilities. Upon arriving at the cocoa processing factory, the dried cacao beans are carefully inspected for quality. Factories use advanced optical sorting machines equipped with cameras and lasers to identify and remove defective beans, such as those that are cracked, moldy, or undersized. Any remaining debris, like stones or twigs, is removed using vibrating screens and air separators. Once the beans are cleaned, they are stored in large silos made of food-grade stainless steel, which protects them from contamination while allowing for easy access as the beans move through the production line. The first step inside the factory is roasting, a critical stage that brings out the rich chocolatey aroma and flavor of the beans. Industrial roasters are designed to handle large volumes of cacao beans, roasting them at precise temperatures that can range from 250 to 300 degrees Fahrenheit. The exact temperature and duration of roasting depend on the type of cocoa powder being produced, as darker roasts develop more intense flavors, while lighter roasts preserve subtle fruity or floral notes. During roasting, the shells of the beans become brittle, and the internal nibs, which contain the cocoa solids and cocoa butter, begin to separate from the shell. Sensors and computer-controlled systems monitor the roasting process to ensure consistency across batches. Once roasting is complete, the beans are rapidly cooled, using air or water to prevent overcooking. The next stage is winnowing, where the roasted beans are cracked open to separate the nibs from the outer shells. This process is carried out using winnowing machines, which use a combination of mechanical rollers and air currents to break the shells and blow them away. The result is a pile of clean, roasted nibs, which are the purest form of cacao and the raw material for all cocoa products. The nibs are then ground into a thick, viscous liquid known as cocoa liquor, despite containing no alcohol. The grinding process involves heavy-duty industrial grinders, such as roller mills or stone grinders, which crush the nibs into tiny particles. This process releases the natural cocoa butter within the nibs, creating a smooth liquid that flows easily. The particle size is reduced to less than 30 microns during this stage to ensure a silky texture. Cocoa liquor is the base ingredient for many chocolate products, but for cocoa powder production, the focus shifts to separating the two main components of the liquor, cocoa solids and cocoa butter. The separation of cocoa solids and cocoa butter is achieved through pressing. Cocoa liquor is fed into hydraulic or screw presses, which apply immense pressure, up to 6,000 pounds per square inch, to squeeze out the cocoa butter. This process leaves behind a solid cake of compressed cocoa solids. The extracted cocoa butter is collected and filtered for use in other products, such as chocolate bars, cosmetics, or pharmaceuticals. Meanwhile, the cocoa cake, which still contains a small amount of residual fat, becomes the foundation for cocoa powder. The cocoa cake is cooled and broken into smaller chunks before being fed into pulverizing machines, where it is ground into a fine powder. Factories use various types of grinding equipment, such as pin mills or ball mills, to achieve the desired particle size for cocoa powder. This step is critical for ensuring that the final product has a consistent texture and dissolves easily in liquids. The fineness of cocoa powder can vary depending on its intended use. For example, baking-grade cocoa powder is typically ground finer than drinking cocoa. At this point, the cocoa powder is almost ready, but one additional process may take place depending on the type of cocoa being produced: alkalization. Also known as Dutch processing. Alkalization involves treating the cocoa powder with an alkaline solution, such as potassium carbonate. This process neutralizes the natural acidity of the cocoa, darkens its color, and gives it a smoother, milder flavor. Alkalized cocoa powder is often used in baking and beverages, as its reduced acidity reacts differently with leavening agents like baking soda. Once the cocoa powder is fully processed, it undergoes rigorous quality control tests to ensure it meets the manufacturer's standards. Samples are tested for flavor, color, pH levels, fat content, and particle size. Factories use advanced laboratory equipment, such as spectrophotometers and viscometers, to measure these properties with precision. Any deviations from the desired specifications are identified and corrected before the product moves to the packaging stage. Packaging is the final step in the production process, and it plays a critical role in preserving the freshness and quality of the cocoa powder. The powder is first sifted to remove any clumps or oversized particles, ensuring a uniform texture. It is then transferred to automated filling machines, which dispense precise amounts of cocoa powder into containers, such as tins, pouches, or bulk bags. For retail packaging, the containers are often flushed with nitrogen gas, before sealing to remove oxygen and prevent spoilage. Labels are applied to the packages, including information such as the brand, product type, lot number, and expiration date. Once packaged, the cocoa powder undergoes a final round of inspections, where advanced vision systems check for defects such as improper sealing, misaligned labels, or damaged containers. The finished products are then packed into cartons or cases using robotic packaging systems. Palletizing robots stack the cartons neatly onto pallets, which are shrink-wrapped for stability and loaded onto trucks or shipping containers for distribution. The process begins with the careful selection and sourcing of raw ingredients. The primary components of KitKat bars include wheat flour, sugar, cocoa mass, cocoa butter, milk powder, vegetable oils, and emulsifiers. Nestlé, the brand behind KitKat, sources these ingredients from various regions worldwide, ensuring sustainability and adherence to strict quality standards. The cocoa used in KitKat is primarily sourced from the Nestlé Cocoa Plan, which promotes sustainable farming practices and fair trade. Once the raw materials arrive at the production facility, they undergo a series of inspections and tests to verify purity, consistency, and compliance with food safety regulations. This includes spectroscopic analysis for contaminants, moisture content testing, and sensory evaluations conducted by trained professionals. Once approved, the ingredients are stored in temperature-controlled silos and dispensing systems. The flour is kept in airtight storage to prevent contamination, while cocoa and milk powder are maintained under controlled humidity conditions to prevent clumping. Automated feeding systems transport these raw materials to the respective processing units, ensuring precise measurement and consistency in formulation. The first major step in KitKat production is wafer baking. The signature light and crispy wafer layers are created through a precise blending of wheat flour, water, sugar, and vegetable oils. Large industrial mixers, equipped with programmable logic controllers, ensure thorough mixing to produce a smooth and homogeneous batter. Once mixed, the batter is transferred via pressurized pumps to high-speed continuous wafer baking ovens. These ovens feature rotating baking plates that evenly distribute the batter across the surface, forming thin sheets of wafer. The baking plates operate at carefully controlled temperatures, typically around 180 to 200 degrees Celsius, ensuring uniform texture and color. The baked wafer sheets emerge golden brown and crisp, ready for the next stage. To enhance the crispness, the wafer sheets pass through a controlled cooling system. Conveyor belts transport the freshly baked wafers through a cooling tunnel, where calibrated fans gradually reduce the temperature to prevent thermal shock. The cooled wafers are then directed to the trimming and cutting station. Automated guillotine cutters trim the edges of the wafers to achieve uniform dimensions, ensuring consistency across all KitKat bars. Once trimmed, the wafers are transported to the layering station. Here, a fine layer of chocolate cream filling made from a precise blend of cocoa, sugar, and milk powder is evenly spread onto the wafers. Automated depositor machines ensure the filling is applied uniformly, maintaining the right thickness for optimal texture. The layering process continues with additional wafer sheets stacked on top, creating a multi-layered wafer slab. These slabs are then pressed under controlled pressure to bond the layers together without crushing the delicate structure. After layering, the wafer slabs proceed to the cutting stage. High-speed rotary or ultrasonic blade systems slice the large wafer sheets into precise rectangular portions, forming the individual KitKat fingers. Ultrasonic cutting technology is particularly effective in ensuring clean, precise cuts without generating excess crumbs or damaging the layers. The next crucial step is chocolate enrobing. The enrobing process begins with the preparation of molten milk chocolate, which is produced in large conching machines. These machines continuously grind and blend cocoa mass, cocoa butter, sugar, and milk powder, refining the mixture to achieve a smooth, velvety consistency. The conching process, which can last several hours, helps develop the rich, creamy texture and enhances the flavor profile of the chocolate. Once ready, the molten chocolate is fed into enrobing machines, where KitKat fingers pass through a curtain-like flow of chocolate. These enrobers ensure complete coverage, with excess chocolate removed using controlled air jets and vibrating conveyors. To achieve the signature glossy finish, the enrobed bars pass through a tempering unit, which carefully regulates the chocolate's crystallization process. This involves a precise cycle of heating, cooling, and reheating to stabilize the cocoa butter crystals, preventing bloom and ensuring a smooth, even texture. Following enrobing, the chocolate-covered KitKat bars enter a cooling tunnel. This tunnel, equipped with multi-zoned cooling technology, gradually reduces the temperature in stages to solidify the chocolate coating without causing cracks or condensation. The cooling process is carefully monitored using infrared sensors to maintain consistency. Once the chocolate is fully set, the KitKat bars move to the quality control and inspection stations. Advanced vision inspection systems, equipped with high-resolution cameras, scan each bar for defects, such as uneven coating, improper sizing, or misaligned layers. Bars that do not meet quality standards are automatically rejected by robotic sorting arms and sent for reprocessing. Additional quality checks include weight verification, moisture content analysis, and sensory testing conducted by trained specialists. After passing inspection, the KitKat bars are transported to high-speed wrapping machines. Individual bars are wrapped in foil or plastic film using heat sealing technology, ensuring airtight packaging that preserves freshness. These wrapped bars are then grouped into multi-packs, which are subsequently boxed using robotic case packers. The packaging design is carefully printed with product details, barcodes, and branding elements before final sealing. The packaged KitKat bars are then palletized for distribution. Automated palletizing systems stack the boxes onto pallets in a precise arrangement to optimize space utilization during transportation. These pallets are shrink-wrapped for stability and loaded onto temperature-controlled trucks for delivery to distribution centers worldwide. The logistics process is carefully coordinated to ensure timely delivery, with real-time tracking systems monitoring shipments from factory to retailer. Throughout the entire production process, extensive quality control measures are in place to uphold product integrity. Each batch undergoes rigorous laboratory testing, including microbiological screening, allergen testing, and texture analysis. Data from all processing stages is logged in automated tracking systems, allowing full traceability and compliance with food safety regulations. While the fundamental principles of KitKat production remain consistent across different manufacturing plants, regional variations may exist to cater to local tastes and preferences. For example, KitKat flavors such as matcha green tea, strawberry, and sake are produced in Japan using specialized formulations. Some factories may also incorporate alternative chocolate blends, varying cocoa content to suit market demands. Nestlé continues to innovate and optimize KitKat production through advancements in automation, sustainability initiatives, and ingredient sourcing. Modern factories are increasingly utilizing AI-driven quality control systems, energy-efficient processing equipment, and eco-friendly packaging solutions to reduce environmental impact. With continuous improvements in manufacturing technology, KitKat remains a global favorite, offering consumers a consistently delightful chocolate experience in every bite. Mars bars, one of the most iconic chocolate confections in the world, are produced in highly sophisticated manufacturing facilities designed to ensure consistency, efficiency, and quality at every step of the process. The production of Mars bars involves multiple intricate stages, from sourcing and processing raw ingredients to forming, enrobing, cooling, and packaging the final product. Each step is meticulously controlled using advanced automation technology and stringent quality control measures to ensure the signature caramel, nougat, and chocolate combination is perfectly replicated in every bar. The process begins with the careful selection of raw ingredients. The main components of a Mars bar include sugar, cocoa mass, cocoa butter, skimmed milk powder, whey powder, palm fat, glucose syrup, lactose, milk fat, and egg whites. These ingredients are sourced from trusted suppliers and undergo rigorous quality assurance checks upon arrival at the factory. Sugar, which plays a crucial role in both the nougat and caramel layers, is stored in large silos, where it is kept dry and free from contamination. Cocoa products, including cocoa mass and cocoa butter, are stored in climate-controlled environments to prevent degradation. Dairy ingredients, such as skimmed milk powder and whey powder, are tested for purity and consistency before use. Once the raw ingredients are approved, the first major stage in Mars bar production is the creation of the nougat layer. Nougat is a key structural component of the bar, providing a soft, chewy texture that contrasts with the caramel and chocolate. The nougat making process begins in large industrial mixing tanks, where a combination of sugar, glucose syrup, and water is heated to create a syrup. This syrup is then aerated using a whipping system, which incorporates fine air bubbles to achieve the desired light and fluffy texture. During this stage, egg whites or hydrolyzed soy protein are added as stabilizers to maintain the nougat's consistency. Once the nougat mixture reaches the proper texture, it is transferred onto a continuous conveyor belt, where it is spread into an even layer. This belt passes through a cooling tunnel to allow the nougat to set before it reaches the next stage of the process. The cooled nougat layer is then precisely cut into rectangular strips using high-speed guillotine cutters. These strips will form the base of each Mars bar. The next step in the process is the caramel layer. The caramel used in Mars bars is created through a controlled cooking process that involves heating sugar, glucose syrup, and milk ingredients to high temperatures. This process requires careful monitoring to achieve the perfect balance of sweetness and viscosity. Industrial batch cookers equipped with automated temperature controls ensure that the caramel reaches the ideal consistency before it is deposited onto the nougat base. The caramel is applied as a continuous sheet over the nougat layer, ensuring even distribution and uniform thickness. Once the caramel is applied, the combined nougat and caramel layers proceed through a controlled cooling tunnel, where the temperature is gradually reduced to allow the caramel to set without becoming too hard or sticky. This ensures that the layers remain cohesive and easy to cut in the next stage of production. After cooling, the layered nougat and caramel sheets are fed into an automated cutting system, which uses precision blades to slice them into individual bar-sized portions. These freshly cut bars are then transported via conveyor belts to the enrobing station, where they receive their final chocolate coating. The enrobing process is a critical step in Mars bar production, as it gives the bars their signature smooth milk chocolate exterior. The chocolate coating is made from a blend of cocoa mass, cocoa butter, sugar, and milk powder, which is carefully tempered to achieve the perfect texture and glossy finish. The tempering process involves heating and cooling the chocolate in a controlled manner to ensure the cocoa butter crystals form a stable structure, preventing fat bloom and ensuring a smooth mouthfeel. At the enrobing station, the cut nougat and caramel bars pass through a curtain-like waterfall of molten chocolate, which fully coats them. Excess chocolate is removed using controlled air jets and vibrating conveyors to ensure an even layer without excessive buildup. Some factories use a two-stage enrobing process, where an initial thin layer of chocolate is applied as a base coat before the final, thicker chocolate layer is added. After enrobing, the chocolate-covered bars enter a multi-zone cooling tunnel, which gradually reduces their temperature in controlled stages. This cooling process allows the chocolate to set properly without developing cracks or a dull surface. The bars emerge from the cooling tunnel with a perfectly set chocolate shell, ready for the final stages of quality control and packaging. Quality control is a fundamental part of Mars bar production, ensuring that only bars meeting strict standards reach consumers. Automated vision inspection systems equipped with high-resolution cameras scan each bar for defects such as uneven coating, misshapen forms, or inconsistencies in size. Bars that do not meet the required specifications are automatically rejected and sent for reprocessing. Additional quality control measures include weight checks using precision weighing systems, texture analysis, and sensory evaluations conducted by trained specialists. Once the bars pass quality inspection, they proceed to the packaging area, where high-speed wrapping machines individually wrap each bar in foil or plastic film. These machines use heat sealing technology to create airtight packaging that preserves freshness and prevents contamination. The wrapped bars are then grouped into multi-packs and placed into branded cartons, which are sealed and labeled using automated case packing systems. The final step in the process is palletization and distribution. Automated palletizing systems stack the packaged bars onto pallets in a precise arrangement to optimize space utilization during transportation. The pallets are shrink-wrapped for stability and loaded onto temperature-controlled trucks for distribution to retail stores and supermarkets worldwide. The entire logistics process is carefully coordinated to ensure timely delivery while maintaining the product's freshness and quality. Throughout the entire manufacturing process, Mars maintains stringent quality control and food safety standards. Each production batch undergoes extensive laboratory testing, including microbial analysis, allergen testing, and moisture content verification. The company also invests in sustainable sourcing initiatives, ensuring that key ingredients such as cocoa and palm oil are responsibly sourced to minimize environmental impact. Different Mars manufacturing facilities may incorporate slight variations in processing techniques based on regional ingredient availability, consumer preferences, or proprietary formulations. Some facilities may use alternative chocolate blends with varying cocoa content to cater to specific markets, while others may modify the nougat formulation for textural differences. Additionally, Mars continuously invests in research and development to improve efficiency, reduce energy consumption, and enhance sustainability in its production processes. With advancements in automation, AI-driven quality control systems, and eco-friendly packaging innovations, the production of Mars bars continues to evolve while maintaining the signature taste and texture that consumers have loved for generations. Twix, one of the world's most beloved chocolate bars, is manufactured using a highly sophisticated and automated process that ensures each bar maintains its signature combination of crunchy biscuit, smooth caramel, and creamy milk chocolate coating. The production of Twix bars occurs in state-of-the-art factories that utilize precision engineering, cutting-edge food processing technology, and rigorous quality control protocols. From the sourcing of raw ingredients to packaging and distribution, every step is carefully orchestrated to guarantee consistency, efficiency, and superior taste. The process begins with the selection and procurement of high-quality raw materials. The key ingredients in Twix bars include wheat flour, sugar, palm oil, cocoa butter, skimmed milk powder, cocoa mass, lactose, whey powder, salt, and emulsifiers. These ingredients are sourced from carefully vetted suppliers who must meet strict food safety and sustainability requirements. For instance, the cocoa used in Twix bars is sourced through Mars' Cocoa for Generations initiative, ensuring ethical sourcing and environmental responsibility. Similarly, the palm oil used in the biscuits and caramel is certified sustainable to reduce environmental impact. Upon arrival at the manufacturing facility, the raw ingredients undergo thorough quality checks before entering the production process. These checks include spectroscopic analysis to detect contaminants, moisture content analysis to ensure freshness, and sensory evaluations to verify taste and aroma. Ingredients that meet the necessary standards are then stored in temperature-controlled silos and storage units to maintain their quality. The first step in the actual production process is the creation of the biscuit base. Twix bars are distinguished by their crunchy, shortbread-like biscuit layer, which requires precise preparation and baking. The process begins in large industrial mixers, where wheat flour, sugar, palm oil, and leavening agents are combined to form a dough. The mixing process is carefully timed to ensure the dough reaches the ideal consistency, firm enough to hold its shape during baking, yet tender enough to create the signature crisp texture. Once the dough is fully mixed, it is transferred to an automated sheeting system. This system rolls the dough into a uniform sheet of the exact thickness required for Twix bars. The sheeted dough then moves to a rotary cutting machine, which stamps out individual biscuit fingers. Each biscuit is precisely cut to ensure uniform size and shape, allowing for seamless assembly in later stages. The cut dough pieces are placed onto conveyor belts and transported into a large industrial baking oven. These ovens operate using a continuous baking system, where the biscuit fingers travel through different heat zones that gradually bake them to perfection. The baking temperature is carefully controlled, typically ranging between 180 to 200 degrees Celsius, 356 to 392 degrees Fahrenheit, ensuring that each biscuit is evenly baked to a golden brown. Advanced infrared sensors monitor the biscuits throughout the baking process, ensuring uniformity in color, texture, and moisture content. Once fully baked, the biscuits pass through a cooling tunnel that gradually reduces their temperature, preventing cracking or breakage. Next, the caramel layer is prepared. The caramel used in Twix bars is made from a precise blend of sugar, glucose syrup, milk, and butter. This mixture is heated in large stainless steel batch cookers, where it undergoes controlled caramelization. The temperature and cooking time are crucial in achieving the perfect consistency, thick enough to stay in place on the biscuit, but soft enough to deliver a smooth, chewy texture. Once the caramel reaches the desired consistency, it is transferred to a continuous depositor system. This machine evenly dispenses a uniform layer of caramel onto each biscuit. The caramel application must be carefully controlled to ensure consistency in thickness across all bars. Any inconsistencies could lead to difficulties in chocolate enrobing or affect the final texture. With the caramel applied, the bars move along the conveyor belt to a cooling station, where they pass through a controlled cooling tunnel. This tunnel gradually reduces the temperature of the caramel, allowing it to set properly while maintaining its soft, chewy texture. After cooling, the caramel-coated biscuits are ready for the enrobing process, where they will be covered in rich milk chocolate. The enrobing process is one of the most critical steps in Twix production. The milk chocolate coating is prepared in large conching machines, which continuously grind and refine cocoa mass, cocoa butter, sugar, and milk powder. This process enhances the texture and flavor of the chocolate, ensuring a smooth, creamy consistency. The chocolate is then tempered, a controlled heating and cooling process that stabilizes the cocoa butter crystals. Proper tempering is essential to achieving the signature glossy finish and preventing fat bloom, white streaks that can appear on improperly tempered chocolate. At the enrobing station, the caramel-topped biscuits pass through a continuous chocolate waterfall. This ensures that each bar is fully coated in an even layer of chocolate. Any excess chocolate is removed using controlled air jets and vibrating conveyors, which help distribute the chocolate evenly without excessive buildup. Some factories employ a two-stage enrobing process, where a thin base coat of chocolate is applied first to ensure better adhesion before the final, thicker chocolate layer is added. Once the bars are coated, they enter a multi-zone cooling tunnel. This tunnel is divided into different temperature zones that gradually reduce the temperature, allowing the chocolate to set perfectly without cracking or becoming dull. The bars emerge from the cooling tunnel with a firm, glossy chocolate coating, ready for the next stage of production. Quality control is a top priority at every stage of Twix production. After cooling, the bars pass through a series of automated inspection systems. High-speed vision cameras scan each bar for inconsistencies in chocolate coating, caramel distribution, and overall shape. Any bars that do not meet specifications are automatically rejected and sent for reprocessing. In addition to visual inspections, quality control teams conduct random weight checks, moisture analysis, and sensory evaluations to ensure that each batch meets Mars's stringent quality standards. Once the bars have passed inspection, they move to the packaging stage. Twix bars are individually wrapped using high-speed horizontal flow wrapping machines. These machines use heat-sealing technology to create airtight packaging that preserves freshness and prevents contamination. The wrapped bars are then grouped into multi-packs, which are sealed in branded cartons using automated case packing systems. After packaging, the final step in the process is palletization and distribution. Robotic palletizing systems stack the packaged bars onto pallets in precise arrangements, optimizing space for transport. The pallets are then shrink-wrapped for stability and loaded onto temperature-controlled trucks for distribution to retailers worldwide. Mars utilizes an advanced logistics network to ensure efficient delivery while maintaining product freshness. Throughout the entire production process, Mars adheres to strict food safety and sustainability standards. Each batch undergoes rigorous laboratory testing, including microbiological analysis, allergen testing, and texture verification. The company also invests in eco-friendly initiatives, such as reducing energy consumption in manufacturing and using recyclable packaging materials. Different Mars factories may employ slight variations in processing techniques based on regional ingredient availability and consumer preferences. For example, some regions may use alternative chocolate formulations with varying cocoa content, while others may adjust the caramel consistency based on market preferences. Additionally, limited edition Twix flavors, such as Twix white chocolate and Twix peanut butter, require modifications in ingredient formulation and processing techniques. As consumer demand for innovative flavors and healthier options grows, Mars continues to invest in research and development to improve Twix production. Recent advancements in AI-driven quality control, robotic automation, and sustainable ingredient sourcing are shaping the future of Twix manufacturing. Despite these innovations, the core principles of precision, consistency, and quality remain unchanged, ensuring that every Twix bar delivers the signature, crunchy, chewy, and chocolatey experience that consumers love. The making of a Hershey's chocolate bar is a complex, highly automated process that combines tradition with cutting-edge technology. From sourcing high-quality cocoa beans to wrapping the final product, every step is optimized for efficiency, consistency, and taste. The journey of a Hershey's bar begins with the careful selection of raw ingredients sourced from around the world. Cocoa, sugar, milk, and other ingredients are carefully tested to ensure they meet the company's high standards before they are transformed into the iconic chocolate bars that have been loved for generations. At the heart of every Hershey's chocolate bar is cocoa. The company sources its cocoa beans primarily from Ghana, Côte d'Ivoire, and Ecuador, regions known for producing high-quality beans with robust flavor profiles. Cocoa farmers in these areas harvest the ripe pods, extract the cocoa beans, and allow them to ferment for several days to develop their characteristic chocolatey taste. Once dried, the beans are shipped to Hershey's production facilities, where they undergo rigorous quality checks. Each shipment is tested for moisture content, flavor consistency, and the absence of contaminants. Only the highest quality beans make it through this stringent selection process. Once approved, the cocoa beans are sent to the roasting stage. Large industrial roasters expose the beans to carefully controlled heat, typically between 120 to 150 degrees Celsius, 248 to 302 degrees Fahrenheit, depending on the desired flavor profile. The roasting process is essential for developing the deep, complex flavors of chocolate. Different roasting profiles are used depending on whether the beans will be used for milk chocolate, dark chocolate, or other specialty products. After roasting, the cocoa beans enter the winnowing process. Specialized machinery cracks the roasted beans and removes the outer husks, leaving behind the valuable cocoa nibs. These nibs contain both the cocoa solids and cocoa butter needed for chocolate production. The nibs are then ground into a thick, dark paste known as chocolate liquor, which contains no alcohol despite its name. This chocolate liquor is the base for all Hershey's chocolate products. For Hershey's classic milk chocolate bars, chocolate liquor is combined with sugar, milk, and cocoa butter. The milk used in Hershey's chocolate is a key ingredient that gives it its distinctive taste. Unlike many European chocolates that use powdered or condensed milk, Hershey's uses fresh milk sourced from dairy farms in Pennsylvania and surrounding states. The milk is pasteurized and condensed before being blended with sugar to create a sweet, creamy base. The next stage in the process is refining. The chocolate mixture is run through a series of steel rollers that grind the particles to an ultra-fine consistency. This refining process is crucial for creating a smooth, melt-in-your-mouth texture. The finer the particles, the smoother the final chocolate will be. Once refined, the chocolate undergoes conching, a critical process that enhances flavor and texture. Conching machines, which resemble large industrial mixers, continuously stir the chocolate at controlled temperatures for several hours. This process aerates the chocolate, allowing unwanted acidic compounds to evaporate while enhancing its creamy mouthfeel. Hershey's uses a proprietary conching method that contributes to its signature flavor, which has a slightly tangy undertone due to controlled acidity in the milk. After conching, the chocolate moves to the tempering stage. Tempering is the process of heating and cooling chocolate in a precise manner to stabilize the cocoa butter crystals. Proper tempering ensures that Hershey's bars have a glossy finish, a firm snap, and a long shelf life. If the chocolate were not tempered correctly, it could develop fat bloom, a whitish streaking effect caused by unstable cocoa butter. Now, the tempered chocolate is ready for molding. Automated machines pour precise amounts of liquid chocolate into bar-shaped molds, which are then vibrated to remove air bubbles and ensure even distribution. The molds travel along a conveyor system into a cooling tunnel, where the chocolate solidifies into its final shape. Once cooled, the bars are ejected from their molds and transported via conveyor belts to the packaging area. Here, high-speed wrapping machines encase each bar in foil and branded paper sleeves, protecting the chocolate from moisture and light while ensuring a fresh, appealing presentation. Throughout the entire process, strict quality control measures are in place. High-resolution vision inspection systems scan each bar for defects, such as air bubbles, improper molding, or size inconsistencies. Bars that do not meet specifications are automatically rejected and sent for reprocessing. Additionally, random sensory evaluations are conducted by trained taste testers to ensure that the flavor, texture, and overall quality remain consistent. Once packaged, The final step is palletization and distribution. Automated robotic arms stack the packaged bars onto pallets, which are then shrink-wrapped for stability. These pallets are loaded onto temperature-controlled trucks and shipped to retailers worldwide. Hershey's operates an advanced logistics network that ensures timely delivery while maintaining product freshness. The entire manufacturing process is designed for efficiency, consistency, and sustainability. Hershey's continues to invest in eco-friendly initiatives, such as reducing water and energy consumption in production, using ethically sourced cocoa, and optimizing packaging materials to minimize waste. Different Hershey's factories may employ slight variations in processing techniques based on regional preferences and ingredient availability. Additionally, specialty products like Hershey's cookies and cream bars or Hershey's dark chocolate require modifications in ingredient formulation and processing times. As the chocolate industry continues to evolve, Hershey's remains at the forefront of innovation, combining tradition with advanced manufacturing techniques to produce its iconic chocolate bars. Through precision engineering, strict quality control, and a commitment to excellence, Hershey's ensures that every bar delivers the same beloved taste that generations have enjoyed. The making of Toblerone, the iconic triangular chocolate bar, is a masterclass in precision engineering, premium ingredient selection, and automated manufacturing processes. Unlike conventional chocolate bars, Toblerone stands out for its distinctive shape, rich Swiss milk chocolate, and the inclusion of honey and almond nougat. Every step, from sourcing the finest ingredients to molding the signature peaks, is meticulously controlled to ensure quality, consistency, and adherence to the Swiss chocolate making tradition. The process begins with sourcing high-quality ingredients. Toblerone's signature flavor comes from its carefully selected components: Swiss milk, sugar, cocoa mass, cocoa butter, honey, almonds, and egg whites. The milk, sourced from Swiss dairy farms, is a critical ingredient that contributes to the creamy texture. The cocoa is sourced from sustainable farms in Ghana and Ecuador, where beans are hand-harvested, fermented, and dried under strict quality control measures. Almonds are procured from select suppliers, ensuring they meet the required standards of size, flavor, and crunch. The honey, a key component that adds a subtle sweetness, is sourced from European beekeepers specializing in high-quality aromatic varieties. Once the ingredients arrive at the production facility, they undergo rigorous quality checks. Advanced spectroscopic analysis, moisture content testing, and flavor profiling ensure that each ingredient meets the brand's high standards. The cocoa beans are then roasted at carefully controlled temperatures to develop their deep, complex flavor. Different roasting profiles are used depending on whether the beans will be used for Toblerone's milk, dark, or white chocolate variations. After roasting, the cocoa beans move to the winnowing stage, where high-powered machinery cracks them open and removes the husks. The remaining cocoa nibs, which contain the essence of the chocolate, are then finely ground into a thick, rich paste known as chocolate liquor. This forms the base of Toblerone's chocolate. The chocolate liquor is blended with sugar, cocoa butter, and Swiss milk powder to create the signature, smooth and creamy chocolate mixture. The next step in the process is refining. The chocolate mixture passes through a series of heavy-duty steel rollers that break down the particles to an ultra-fine consistency. This is crucial in achieving the signature melt-in-your-mouth texture. The refining process also helps blend the ingredients evenly, ensuring a perfectly smooth mixture. Following refining, the chocolate undergoes conching, a process that enhances its texture and flavor. Large conching machines continuously mix, aerate, and heat the chocolate for several hours, allowing volatile acids to evaporate and the flavors to develop fully. Toblerone's conching process is fine-tuned to create a silky texture and a well-rounded, rich taste. Meanwhile, the honey and almond nougat mixture is prepared in a separate area of the factory. Sugar, honey, and egg whites are heated and aerated to create a light, chewy nougat. Almonds, which have been roasted to bring out their nutty aroma, are chopped into small pieces and folded into the nougat mixture. The nougat is then cooled and ground into fine pieces before being incorporated into the chocolate. Once the chocolate has completed the conching process, the finely ground nougat mixture is carefully folded into it, ensuring even distribution. This step is crucial in maintaining the signature texture and taste of Toblerone. With the chocolate and nougat mixture fully blended, the next stage is tempering. Tempering is a precise process of heating and cooling chocolate in a controlled manner to stabilize the cocoa butter crystals. Proper tempering ensures that the chocolate has a glossy finish, a firm snap, and a smooth texture. Toblerone's tempering process is carefully calibrated to achieve the ideal consistency before molding. Molding is where Toblerone's iconic shape comes to life. The tempered chocolate is poured into custom-designed triangular molds that give the bar its distinctive peaks. The molds are gently vibrated to remove air bubbles and ensure even distribution of the chocolate. After molding, the bars pass through a cooling tunnel, where they are gradually cooled to allow the chocolate to set perfectly without cracks or imperfections. Once solidified, the bars are removed from the molds and transported to the quality control station. Each bar is inspected using high-resolution vision cameras, which detect any inconsistencies in shape, texture, or coating. Automated sorting systems remove any defective bars, ensuring that only perfectly shaped Toblerone bars proceed to packaging. The packaging process is designed to maintain the freshness and integrity of the chocolate. Toblerone bars are individually wrapped in foil to protect them from moisture and light, then placed into the iconic triangular cardboard cartons. High-speed packaging machines fold and seal the cartons with precision, ensuring that the bars remain securely enclosed. Following packaging, the bars are palletized using robotic systems, stacked carefully for stability during transport. These pallets are shrink-wrapped and loaded onto trucks for distribution to markets around the world. Temperature-controlled logistics ensure that the chocolate remains in perfect condition during transit. Throughout the entire manufacturing process, Toblerone maintains strict quality control measures. Each batch undergoes laboratory testing, including texture analysis, microbial screening, and taste assessments conducted by trained specialists. Data is continuously logged in automated tracking systems, allowing for full traceability of every Toblerone bar produced. Different Toblerone manufacturing facilities may employ slight variations in processing techniques depending on regional ingredient availability and market preferences. Specialty editions, such as Toblerone White Chocolate or Toblerone Dark, require slight modifications in ingredient formulations and processing steps. As consumer preferences evolve, Toblerone continues to innovate while maintaining the brand's heritage of Swiss chocolate craftsmanship. Investments in sustainable cocoa sourcing, eco-friendly packaging solutions, and advanced automation ensure that Toblerone remains a global favorite while reducing its environmental footprint. Through precision engineering, time-honored techniques, and a commitment to quality, every Toblerone bar delivers the signature taste and texture that chocolate lovers around the world cherish. The production of Snickers, one of the world's most popular chocolate bars, is a highly automated and meticulously controlled process designed for efficiency, consistency, and large-scale output. With its signature combination of nougat, caramel, peanuts, and milk chocolate, Snickers is produced in state-of-the-art facilities that use cutting-edge food processing technology, ensuring that every bar meets the brand's high-quality standards. From sourcing the finest raw ingredients to packaging and distribution, every step is optimized to deliver the same taste, texture, and satisfaction in every bite. The journey of a Snickers bar begins with the careful selection of raw materials. The main components include sugar, peanuts, milk powder, cocoa mass, cocoa butter, palm oil, glucose syrup, egg whites, and emulsifiers. These ingredients are sourced from carefully vetted suppliers, ensuring compliance with strict food safety and sustainability standards. Mars, the company behind Snickers, prioritizes responsible ingredient sourcing, ensuring that cocoa is ethically obtained through its Cocoa for Generations program, which promotes fair labor practices and sustainable farming methods. Peanuts, another crucial ingredient, are primarily sourced from the United States, where they are grown under controlled conditions to maintain size, flavor, and crunch. Once the ingredients arrive at the manufacturing facility, they undergo a rigorous quality control process. Each batch is tested for moisture content, purity, and potential contaminants. Peanuts, in particular, go through an additional inspection phase, where they are sorted by size and quality. High-speed optical sorting machines remove any defective or discolored peanuts, ensuring that only the best nuts make it into Snickers bars. The first major step in the Snickers production process is creating the nougat base. Nougat provides the chewy texture that forms the foundation of the bar. It is made by combining sugar, corn syrup, and water, which are heated in large industrial cooking vats to create a syrup. This syrup is then aerated using high-powered whipping machines, which incorporate fine air bubbles, giving the nougat its characteristic light and chewy texture. Egg whites or soy protein are added as stabilizers to help maintain consistency. Once aerated, the nougat is spread onto a moving conveyor belt in a continuous sheet, where it is allowed to cool and set. This process is carefully controlled to prevent the nougat from becoming too hard or too soft. Automated guillotine cutters then slice the nougat sheet into uniform rectangular portions, ensuring that each piece is the exact size required for Snickers bars. Next comes the caramel layer. The caramel in Snickers is made from a blend of sugar, glucose syrup, milk, and butter, which is heated in large stainless steel batch cookers. The temperature is carefully monitored to achieve the perfect viscosity, thick enough to hold its shape, but soft enough to provide a smooth, chewy texture. Once cooked to perfection, the caramel is poured in a controlled stream onto the nougat base. The caramel-covered nougat passes through a cooling tunnel, where it sets just enough to be firm, but still pliable. Now it's time to add the peanuts. Before being incorporated into the bars, the peanuts are roasted in industrial ovens to enhance their flavor and crunch. After roasting, they are cooled and evenly distributed over the caramel layer using precision peanut dispensers. These machines ensure that each bar receives the right amount of peanuts, maintaining uniformity across all Snickers bars. Once the peanuts are in place, the layered nougat, caramel, and peanut sheet moves to the cutting stage. High-speed rotary blades slice the continuous sheet into individual bar-sized portions. Each cut must be precise, ensuring that the caramel and nougat layers remain intact while maintaining a consistent size. The next critical step is chocolate enrobing. The milk chocolate coating used for Snickers bars is made from a blend of cocoa mass, cocoa butter, sugar, and milk powder. This mixture is refined and conched in large machines that continuously grind the chocolate to achieve a smooth texture. The chocolate is then tempered, a process that involves controlled heating and cooling to stabilize the cocoa butter crystals. Proper tempering ensures a glossy finish and prevents fat bloom, which can cause chocolate to develop a dull appearance. At the enrobing station, the cut bars pass through a waterfall of liquid milk chocolate, fully coating them. Excess chocolate is removed using controlled air jets and vibrating conveyors, ensuring an even layer without excessive buildup. Some factories use a two-stage enrobing process, where a thin base coat of chocolate is applied first to create a stable foundation before the final. Thicker chocolate layer is added. After enrobing, the bars enter a multi-zone cooling tunnel. This tunnel gradually lowers the temperature in controlled stages, allowing the chocolate to set properly without developing cracks or dull spots. Once fully cooled, the Snickers bars emerge with a perfectly solidified chocolate coating, ready for quality inspection. Quality control is a critical component of Snickers production. Each bar undergoes a series of automated inspections to ensure that it meets strict specifications. High-speed vision inspection systems equipped with high-resolution cameras scan each bar for defects such as uneven coating, improper size, or misshapen layers. Any bars that do not meet the required standards are automatically rejected and sent for reprocessing. Additional quality checks include weight verification, moisture content analysis, and sensory testing conducted by trained specialists. Once the bars have passed inspection, they move to the packaging stage. Snickers bars are individually wrapped in plastic film using high-speed horizontal flow wrapping machines. These machines use heat sealing technology to create airtight packaging that preserves freshness and prevents contamination. The wrapped bars are then grouped into multi-packs and packed into branded cartons using automated case packers. The final step in the process is palletization and distribution. Automated systems stack the packaged cartons onto pallets in precise formations, optimizing space for transport. These pallets are then shrink-wrapped for stability and loaded onto temperature-controlled trucks for distribution to retailers worldwide. Snickers bars are shipped to over 70 countries, requiring an advanced logistics network to ensure that they arrive fresh and in perfect condition. Throughout the entire production process, Mars maintains stringent food safety and sustainability practices. Each batch undergoes extensive laboratory testing, including microbiological screening, allergen testing, and texture verification. The company also invests in sustainable ingredient sourcing, reducing its environmental footprint through energy-efficient manufacturing processes and eco-friendly packaging solutions. Different Snickers manufacturing facilities may employ slight variations in processing techniques based on regional ingredient availability and consumer preferences. For example, some regions may use alternative chocolate blends with varying cocoa content, while others may modify the nougat or caramel consistency based on market demands. Additionally, special edition Snickers bars, such as Snickers Almond or Snickers Peanut Butter, require modifications in ingredient formulation and production methods. As consumer preferences evolve, Mars continues to innovate while maintaining the classic Snickers taste and texture. Advancements in automation, AI-driven quality control, and sustainable manufacturing practices are shaping the future of Snickers production. Despite these innovations, the fundamental principles of precision, consistency, and quality remain unchanged, ensuring that every Snickers bar delivers the same delicious combination of chewy nougat, gooey caramel, crunchy peanuts, and smooth milk chocolate that has made it a favorite among chocolate lovers worldwide. The production of Tony's Chocolonely chocolate bars is a carefully designed process that emphasizes ethical sourcing, sustainability, and high-quality chocolate-making techniques. Unlike traditional chocolate brands, Tony's Chocolonely is dedicated to creating a slave-free chocolate industry, ensuring that every step in the supply chain is transparent and fair. From sourcing cocoa beans from cooperatives in West Africa to molding and packaging the final bars, the production process is a seamless blend of traditional craftsmanship and modern automation. The journey of a Tony's Chocolonely bar begins with cocoa sourcing. The company partners with cooperatives in Ghana and Côte d'Ivoire, regions that are known for cocoa production, but also face significant challenges related to child labor and unfair wages. Tony's Chocolonely implements direct trade practices, paying a premium for cocoa and providing additional support to farmers through training programs and financial resources. This ensures that the beans are ethically sourced while maintaining a high standard of quality. Once harvested, The cocoa beans go through a meticulous post-harvest process. Farmers ferment the beans for several days, a crucial step that develops the deep, complex flavors needed for premium chocolate. After fermentation, the beans are spread out under the sun to dry, reducing moisture content and preventing mold growth. When dried to the appropriate level, the beans are packed into jute sacks and shipped to Tony's Chocolonely's processing facilities. Upon arrival at the factory, the beans undergo rigorous quality control checks. Samples from each shipment are tested for moisture levels, flavor consistency, and potential contaminants. Beans that pass inspection are stored in climate-controlled silos to maintain freshness before entering the production line. The first step in the chocolate-making process is roasting. Large industrial roasting machines heat the beans at precise temperatures, usually between 120 to 150 degrees Celsius, 248 to 302 degrees Fahrenheit. This process enhances the natural chocolate flavors and eliminates unwanted bitterness. The roasting time and temperature depend on the type of chocolate being produced. Dark chocolate requires a slightly longer roasting process than milk chocolate to develop its rich, bold flavors. Once roasted, the beans enter the winnowing process. A specialized machine cracks open the roasted beans and removes the outer husks, leaving behind the valuable cocoa nibs. These nibs contain both cocoa solids and cocoa butter, the essential components of chocolate. The nibs are then ground into a thick, smooth paste known as chocolate liquor. This process, carried out by industrial grinders, reduces the particle size of the nibs, creating a velvety consistency. At this stage, different chocolate variations begin to take shape. For Tony's Chocolonely's milk chocolate bars, the chocolate liquor is combined with sugar, milk powder, and additional cocoa butter to create a creamy texture. For dark chocolate, higher cocoa percentages are used with less sugar and no milk. The next step in the process is refining. The chocolate mixture is passed through heavy-duty steel rollers that grind the ingredients into ultra-fine particles. This step is crucial for achieving the smooth texture that defines high-quality chocolate. The finer the particles, the better the melt-in-your-mouth experience. Following refining, the chocolate undergoes conching, a process that enhances both texture and flavor. Large conching machines continuously mix and aerate the chocolate for several hours, allowing any residual acidity to evaporate while intensifying the chocolate's richness. The conching time varies depending on the desired flavor profile. Longer conching results in a smoother, more developed taste. After conching, the chocolate is tempered, a precise heating and cooling process that stabilizes the cocoa butter crystals. Proper tempering ensures that Tony's Chocolonely bars have a glossy finish, a satisfying snap when broken, and a long shelf life without developing fat bloom, the white streaks that can appear on improperly tempered chocolate. Once tempered, the liquid chocolate is ready for molding. Unlike most chocolate bars, Tony's Chocolonely bars are intentionally molded in an uneven pattern, symbolizing the unequal distribution of wealth in the chocolate industry. Automated machines pour precise amounts of chocolate into these custom-designed molds, which are then gently vibrated to remove air bubbles and ensure even distribution. The molds are then transferred to a cooling tunnel, where the chocolate gradually solidifies under controlled temperatures. This process prevents the bars from developing surface defects and ensures that they retain their perfect shape. Once the chocolate has fully set, the bars are ejected from the molds and sent to the quality control station. High-speed vision inspection systems scan each bar for defects, such as air bubbles, improper molding, or uneven texture. Any bars that do not meet the required standards are removed from the production line and either reprocessed or discarded. After passing quality checks, the bars move to the packaging stage. Tony's Chocolonely uses brightly colored, easily recognizable wrappers, each featuring bold typography and branding. The packaging process is fully automated, with high-speed wrapping machines, sealing each bar in foil and paper to protect it from moisture and contamination. The wrapped bars are then packed into cartons using robotic case packers. The final step in the process is palletization and distribution. Automated robotic systems stack the packaged bars onto pallets in a precise arrangement, optimizing space for transport. Manufacturing Almond Joy candy bars on an industrial scale begins long before any chocolate is melted or coconut is mixed. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components, the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then graded using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase, designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth, and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every Almond Joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for Almond Joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated, separated into single file, and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking, and an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the Almond Joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit, and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor, and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the 1/10 of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coder, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable. Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coded, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final check weigher ensures that the total weight of each carton falls within specification, and the completed units are then moved down the line to case packing. The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermal loggers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from Coconut Grove to grocery store, can be completed in just a matter of weeks, but every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability, regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. Trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers. And the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final package.